Yeah, and now we are recording. So, yeah, our speaker today is Daniel Gonçalves, and he will talk about subshift algebras. So please, Daniel, go ahead.
Okay, so thank you, Willie. Thank you, Gisela, too, for the invitation. It's a pleasure to speak here. And today I'll be talking about subshift algebras, which is recent work with Giuliano Boava, Gilles de Castro, and Danny Van Wyk. Okay, so I'll talk a little bit. I'll explain a bit the motivation of why we define these algebras, and as the name that we get, subshift algebras, they are really connected with symbolic dynamics. So let me just start the motivation with the very basic of where symbolic dynamics start. Then we have a dynamical system, T of X, just a map from a space to a space. You can code it using sequences in an alphabet. So let's say you just have a map from the unit square to the unit square. We could say that. Just have a map from the unit square. Here, let's say this is S, the square, and you just have a map T from S to S. And when you're studying dynamical systems, you're interested in the orbit of this map, right? So of the points. So the orbit being, you take a point X and you iterate it. So Tx, you do then T of X, and you do T square of X, and so on. So one way of seeing this, say you have a map from the square to the square, you can like partition the square in some pieces. Let's say you can cut it like in 4 pieces here. 1, 2, 3, 4. And okay, look, so I say I start with my point X, say it's here. So this is my point X. And then I look at T of X, well, maybe it's here, T of X. And then T square of X might be here, and so on, right? So then you have a map that take this point to, well, let's say T cube of X is on 2 here again, it could be, right? So I have this T cube of X. So I have this will go to 1, T of X was in 2, then I had 3, and then I had 2 again, okay? So if I want to study the dynamics of this and see, okay, that's the orbit of X, what happens to the orbit of T of X? So if I apply T here, well, you'll just have T of X, T square of X, T cube of X, and so on, right? So if I follow this idea that I just had of how to code this orbit, well, this orbit now is sent to what? I start on T of X, so this little square 2. So 2, 3, 2, and so on. So what I did here, I just erased the first entry. So this is just a shift map, right? That's what we call the shift map. We're just erasing the first entry, and we are coding the dynamics of this map T. And so one way of studying the dynamical systems is just studying now this shift map on infinite sequences over some alphabet. Also, I don't need to, sometimes, right, it could be that if I fall on the, let's see here, on square 3, I can only follow by 2. Let's say it could be that this map is such that if I fall on 3, I will be forbidden to follow 3. You know, once you're here on 3, you never fall on 4, or you never fall on 1. So you'll never see in your infinite sequences this forbidden blocks. You just have infinite sequences with 0, 1, 2, 3, and 4, but this 3 and 4, 2, 1 will never appear. Okay, so these are usually the subshifts. Okay, so in the standard dynamical systems, we study the product of the alphabet A, which is usually a finite set, and subshifts is like you choose a finite collection of forbidden words, and you look at the subshift XF of all infinite sequences where these finite blocks here, forbidden ones, do not appear. Okay, so that's the usual setting. put my watch here. So in the infinite alphabet, if you have an infinite alphabet, right, you could partition this in infinite subsquares, right? Oh, by the way, here you just put like the discrete topology on the alphabet and then just the product topology, okay? That's the usual thing when the alphabet's finite. But once you are in the infinite alphabet case, then things are a little bit different because you can just do this, just get say the naturals as your alphabet, put the discrete topology and take the product topology. That's the more usual thing. But the space that you get are not compact, not even locally compact. And for us, there are like, for people who like sister algebras, this space is not really connected to any sister algebra we know. Maybe there is, right? It is a polished space, but it's not like, you know, we have all this connection between the symbolic dynamics and sister algebras or Leavitt path algebras. And it's not just the product topology in the infinite alphabet space. So I had this before saying recently, but it's been 10 years now, that Ott-Tomforde-Willis, they proposed a definition of shift spaces. And they showed that in the case of graphs, if their shifts are isomorphic, then the graphs sister algebras are isomorphic. But so we wanted to kind of deepen this connection. So, and we wanted some definition, right, that we could encompass the Ott-Tomforde-Willis definition. We could work for graph algebras and could work also for infinite matrices, right, for the graphs coming from infinite matrices. So what our algebras will have like really a strong connection with Ott-Tomforde-Willis subshifts. So I will remind you or like present what's the Ott-Tomforde-Willis shift. Okay. So we start with an infinite alphabet. If you want, you can take A as the natural, no problem. And if you just put the discrete topology, this is not compact. So we look at its compactification, 1-point compactification. I know that okay. So we start with 1-point compactification. So now this is compact. And if I look just at the product here, the product of A tilde, this 1-point compactification, this is a compact space. People in symbolic dynamics really like compact spaces. But now I have a shift that has this extra symbol, infinity, right? This infinity, well, this is kind of exogenous, right? We don't want it there in the shift. So we put an equivalence relation where in the sequences, if it is, I have x1, x2, and there's no infinity, the symbol infinity does not appear, then the equivalence class is just itself. We don't do anything. But if I have a sequence where some infinity symbols appear, I don't know, x4, x5, and infinity, what we do here, we cut at this first infinity that appears, right? And I say this is equivalent to any other sequence that has the same beginning here, x1, x2, x3, infinity here, and anything else after, right? So I just look a sequence that repeats the first n entries that are not infinity and agree in the next entry just infinity. So really what I'm doing, I'm just cutting this here. I'm just looking at the finite sequences in my alphabet. So the full shift is really going to be just all the infinite sequences together with finite sequences, okay? But now with which topology? And then you put the quotient topology here now, okay? So you have like a compact space and you put the quotient topology, which is usually not nice, but here is not bad. You'll see this is actually, you know, totally disconnected, base of Kloppen sets. Oh, that's what that means. It's a nice counter set, okay? And we have this empty sequence, right? We just have this empty word. I have the shift map, which is continuous, except at this empty sequence. Okay. So we want to study subshifts, right, of Ott-Tomforde-Willis. So as before, I want to start with a set of forbidden words. And now I want to define a subset of the Ott-Tomforde-Willis full shift. So what I do First, I look at the infinite sequences, just as the standard way. We'll just look at the infinite sequences such that no block of X appears in the list of forbidden words. But then I wonder which finite sequences should I add? And the idea is really, you're really taking the closure of these infinite sequences, okay, inside the Ott-Tomforde-Willis of that topology. So that is, you just take all the finite sequences that you can extend, just the first letter, you can extend it and follow it by an infinite sequence in your shift. Then you're gonna add it if you have infinitely many, right, ways. So if you have an X here, if you have infinitely many ways to extend it to an infinite sequence in the shift, then you include this finite sequence. Okay, and the associated subshift is just, right, the union of the infinite sequence and the finite one. Okay, so if I have an example here, let's say you have a graph, a labeled graph here. So the alphabet will be just all the labels of the edges. At vertex C here, I'm saying that I have infinitely many edges here. That's what it's standing for. And if I look at edge at the word 7 here, okay, just this word 7, just this edge 7. Well, there are infinitely many edges that I can follow it by, right? But this infinite here is, I could name them, I don't know, E1, E2, E3, and so on. So there are infinitely many ways that I can follow this 7, EI here, that I can follow by infinite sequences, right? EI, and then I can do 8, and I can do 7, 8, 7. So there are infinitely many here, infinitely many possibilities, okay? So the word so 7 here belongs to the subshift, okay? And this quotient topology that I said before, that is kind of mysterious, that I didn't say what it was, for the subshift, is just really on infinite sequences. It's just the usual cylinder sets, right? Just have the usual cylinder sets if you have an infinite sequence. And you're looking at, so we need a neighborhood for a finite sequence, like this, a neighborhood of 7 here that we just defined, okay? So what we do here is we choose a finite collection of edges that follow 7 that we don't like. For example, this F here that I have in the definition, this Z of alpha F, from the finest Z of 7F. Okay. And well, then I just look at all the elements of the shift that start with 7, so the usual cylinder set, and avoid this finite set of edges. So I can have 7, I don't know, E4, E4, 8, and so on. Anything that I start with 7, avoid this finite subset, and go on, okay? And are in the subshift. By the way, in this case, the elements that I have, well, we can check that for a graph or a label graph, the subshift consists of all the infinite paths and the finite path that end in an infinite emitter, right? Because then I'll have infinite ways of following. Okay, right? So, so this is Ott-Tomforde-Willis subshifts, crash course. That's something that I actually worked a bit on them. I always find them appealing, but as I said, we wanted to find an algebra here that can really connect the subshifts and also generalize the standard relation, right, between algebras and the standard subshifts when you just have a finite alphabet and the product topology. So if you just have a finite graph like this one, right, we have the subshift is just all the infinite paths that I can go doing the graph. There's something here that I know there is maybe this. No, that's not it. Anyways, I know that somewhere here there is something that I can highlight things, but there's an infinite path here. I can just Okay, no, I don't know what I don't know. Sorry, just a second. Here, there. Okay, so all infinite paths that I can find in this graph, that's just the shift space. The alphabet has its discrete topology, and they just have the product topology. That's the standard one. And then Leibniz path algebras, I think people know. Just right, you have a graph, and then a sister. Sorry, it's a universal algebra generated by vertices, edges, E star subject to the standard relations. And for us, there in Florianopolis, right, we really like partial actions. So we like to connect, to see this as the Leibniz path algebra as this Q ring associated to a partial action. So given a graph, we look at all the set of infinite paths, look at the free group on the edges. This can also be done into a groupoid or inverse semigroup. Doesn't need to be something as large. But for this talk, we take the free group on all the edges. And so we have a partial action, right? So it's suppose an action of a group, for each element of the group will have a bijection between x, right? Now here in a partial action, actually, I have to pick some subsets of x and define a bijection between these subsets. And, okay, so for us, my subsets, I'm particularly interested in paths A and B that end at the same range. And then I look at all paths in the graph here that begin with A. Let's say I have a graph here, and I have all xab minus 1, all paths that begin with A. And then I have a map, xb minus 1 to xb a minus 1, which just does what? I have an xi here. I just erase this A and I place a B in front, right? Because this psi here is in the follower set of A, which is the same as the follower set of B. So this is a map here, HB A minus 1. And okay. And this action now, which was in just this set action, I could also see as topological one if I want, but induces an action on the functions level, which here I'm having continuous functions. Could also be just the functions generated by the characteristic functions of these sets, right? The standard contravariance here. Just have in a function just composed with the H inverse. And then I do this Q ring associated to it, or the cross product, partial cross product if I want the sister algebra, this Q ring to get the Leibniz path algebra, right? All direct sums of this form, Ft is just all direct sums of the continuous function of those subsets. And we have the multiplication is given by this here. Okay, I don't want to get too detailed to this, but the theorem is that we can see the Leibniz path algebra as this Q ring. Okay, so now we're going to take that and try to define an algebra associated to subshift, right? Using those ideas. So just to set up notation, we start with an alphabet and just the shift map on the infinite sequences. Okay. So I have talked about topology and things, but now we just the data that we start, an alphabet, infinite sequences, just the standard shift map raising the first entry. Right? We call, I already used, but words and blocks are just, or blocks are just the finite words here. And we are given a set of forbidden words. Okay? Given a set of forbidden words. And then we define the subshift. It's just all sequences that no word of X is in the set of forbidden words. That's all that we're given. There's no topology, it's just the set really as general as possible. And okay, the language is all the set of blocks that appear in some element of the shift, or the union of all blocks that appear in some word of, in some sequence of X. This is just standard terminology. So we wanted to define the subshift algebra, right? So we start with a subshift for an alphabet A, and well, what happens here? Look, the definition of this algebra will rely on this set C alpha beta. So when I had before there the partial action, right? I had two arrows connecting here, and let me try to see. Let's say beta and alpha, and I had something here in the follower set, the x, right? And then we had the x, let me try here, beta alpha minus 1 was all the elements that start with beta, and I could erase the beta and put alpha in front. But anything that follows beta here also, right, this x also follows alpha. If I'm in a general shift, this might not happen. Look, I could have a beta here, and I could have now maybe, this could be the same graph, right? I could just go here, and I could have a gamma here, and I could have then, say, followed by a y, different, in a labeled graph, for example. Then, if I define x beta alpha minus 1, I cannot define as all paths that start with beta, because this has beta x, okay, but when I go and look at beta y, this would be a problem. I cannot just erase beta and put alpha in front of y. I can only put gamma in front of y, right? So we have to keep track of this in the subshift algebra. It's more subtle. So when I define a C of alpha beta, I'm looking at the cylinder of beta, so everything that starts with beta, but also that once I erase this beta, right? Once I erase the beta, I can put the alpha in front, okay? So in our example here, C of alpha beta will be just beta x, and will not have the beta y, right? So, and this connects to the follower sets, right? Before, everything had the same follower set, which was just the projection on the vertex, right? Range of beta was equal to the range of alpha. They had the same range, and the follower set was just the same. And we had this projection of this follower set in the algebra. But now we're going to need the projection for each one of these elements, for each of these specific elements, okay? So, well, this is just there's just some comment here that when you take some element to be the empty word, you get the follower set, or just get the usual cylinder. They're all here in this element. Okay.
So omega is the empty word. Then.
Yes, omega is the empty word. Yeah, sorry, I should have said that. Yes, yeah. So if I take alpha omega here, then it's just really the follower set of alpha. Okay. So as I said, we're going to associate to each one of these elements here a projection in the algebra. So we actually, and then we're going to multiply these elements in the algebra, right? So what happens to them when we sum them or we multiply them? So there's some new elements that are going to appear. So we need to consider the Boolean algebra of all generated by this C alpha beta, right? Which is just all the all finite unions, finite intersections, and complements of these sets. If right, you can describe them as finite union of elements of this form. I know it doesn't look good, but usually what we do is just when we work with the algebra, you prove things for C alpha beta, and then you kind of show that that the property is respected by unions or intersections or complements. So how to define the algebra? Okay, so it's again a universal algebra generated by a projection for each of these elements in that Boolean algebra, and a partial isometry for each element of the alphabet, and subject to some relations. So the projections have the expected relations. Projection of the whole space is 1, so it's a unital, right? It's the unit. Projection of the intersection is the product of the projections, and the union, projection of the union is the kind of the disjoint union here, right? All the nice properties of the projections here associated to the Boolean algebra elements. The second is really saying that each SA star is a partial isometry. The third one, well, that's which maybe a little bit more tricky. It's connecting us the S's with the P's. So if you look at S beta, S alpha star, S alpha, S beta star, if you look from that point of view of being each S beta can be represented by the map that adds beta in front of a path or a sequence, or the star erases beta if it starts with beta, then when we apply this in an element of the subshifts, say, I would check if this C here starts with B, right? If possible, if it starts with B, I would erase this B, right? So that's what this SB star would do. It would just erase the B. Then I'll check, okay, S alpha, I'll check if I can put the alpha in front. Okay, if I can put alpha in front, I'll put it on front. And then I will erase because I had the star. And I'll put the B again, right? I'll put it back the beta back in front. So it's really, right, I'm just checking here if this element is in the C of alpha beta, right? I'm just checking if it starts with beta, and if when I erase beta, I can place alpha in front. So this is really what this relation is saying, right? So it's not like unexpected or anything.
Is there, so do the S, I suppose that the S alphas form a semigroup, an inverse semigroup, and is this the universal algebra for a tight representation of the semigroup?
The S alphas, okay. I think we need something else. I think we
the
need
alphas and the P's, so that
yeah, the alphas and the P's, yeah, with the P's. I believe so. If the P's, I believe so. Okay, so so this is just a comment that if we can do S alpha star, S alpha star, S alpha, and you get the projection of the follower set of alpha, which is if you're in a Leavitt path algebra, right, and you just get alpha here and you get a vertex, S alpha star, S alpha is just the range of alpha, the projection of the range of alpha, which is really the projection of the follower set of alpha, right? So this is agreeing here with the usual definition of Leavitt path algebra. Okay. Okay, so this is the algebra, right? So this is algebraic version of Carlsen algebra for C-star algebras, right? So Carlsen, there's a little history on defining this C-star algebra associated with a subshift. There's more than one version, but I think this agrees with the final version which people use now, which was originally defined by Carlsen. But in the infinite alphabet case, our algebra is a generalization for the C-star algebra defined by Carlsen. He only defined it for the finite alphabets. And we decided to make us separate papers. We're actually working right now on the C-star algebra case and doing, right, we have to check a few things that things go through. Okay, so as I said, so I wanted to connect, right, this algebra with the Ott-Tomforde-Willis subshift. So let's go back once more in the subshift case, when we had an infinite alphabet and we had a set of forbidden words, and we denote XOTW by the corresponding Ott-Tomforde-Willis subshift. Okay. Okay, R here is in the composable ring. You can just think of it as a field. No problem. But then if you look at this commutative algebra, which is standard, right? I think it connects what Willie was asking. If you look at this plan of the S alpha star, where alpha elements the language, this is a commutative the commutative algebra, and we show that it's actually isomorphic to the locally constant functions with compact support on the Ott-Tomforde-Willis subshift. Okay.
The composable means that it has no non-trivial idempotency.
No non-trivial, non-central, right?
No centralized importance.
Zero.
That's is that the definition?
Yeah, I always have to. Just 1 second here. Yes. Where was that? The only central idempotents, yes. The only central idempotents are 0 and 1. Yes. Exactly. This is really okay. So we just need this. I'll give an idea of the proof of this. So let's just denote by A. We just need the decomposable ring to see that the image of a homomorphism of a projection, it has to be 0 and 1, right? If I have a homomorphism and apply in a projection, it has to be 0 and 1. That's where we use this. So let's take A to be, well, the span of S alpha star, and we want to show that this is unital because S omega star is in there, right? And what we want to show is that this A is isomorphic or conjugate to LC of let's say A hat R, where A hat is the character space. Okay? A hat is the character space. In fact, I'm just going to say this as a statement. This follows from stone duality. It's something that we do in our paper for sister algebras. It's well known. If you have a commutative sister algebra, then it's right. It's C of X for some X locally compact, and this X is the character space, the space of homomorphisms. But for some, if you just have an algebra which is nice enough, which is the case of this one, then we also prove this also holds. And we have to identify what is this space of homomorphism here. So we're saying that this coincides with the Ott-Tomforde-Willis subshifts. So really the idea follows from this following claim, which is really simple, is that if you have a character, right, and when you apply that S alpha star, if that's equal to 1, then it has to be 0. Any other S beta star that has the same length, if beta has the same length of alpha. Right, for all beta different than alpha, such that beta has the same length as alpha. Okay, and well, moreover, I'm really rusty with writing on the moreover. If you have an initial segment of alpha, if alpha is equal to gamma alpha prime, then phi of S gamma star is also equal to 1. Okay. Well, just to see one of this, so we wanted to see that this phi of S alpha star is 1. Then for the other S beta star is 0. It's just really writing phi of S beta star. Well, if this is 1 here, I can just multiply by 1. S alpha star phi of S beta star. Now phi is a homomorphism. So this is just going to be phi. We can just put things inside S alpha star S beta, and this now is 0, right? S alpha star S beta is 0, beta star, and this is equal to 0. Okay, so for any S beta star here, you get 0 if it's not alpha. Okay. And similar way, you can get this thing here for the initial segment, right? You can just note that if 1 is equal to phi of S alpha star, and then you can just write this as phi of S gamma star, S alpha star. Right. So from here, you just open it up. So this has to be 1, right? You just open, use this as a homomorphism. And so this one has to be 1 too. Okay. Right. Okay. So that was the claim. It's proved. So how do we define now, given a homomorphism here? I want to define a sequence, finite or infinite or finite, but I need to define a sequence. So what we do is, given this phi in a hat, we let n to be equal to the supremum over all the natural numbers, such that, well, there is an alpha in the language, such that this alpha has length n, and phi of S alpha star is 1, is equal to 1. So we take this n as the supremum, and now we can just okay, I don't have, I should have left 2 pages. Okay, so now if n is infinity, then we can just define a map, let's say C of phi to be an infinite sequence, y1, y2, y3, and so on, where y1 up to yi is the unique block such that phi of y1 up to y star such that phi of y1 up to yi and the S of y1 up to yi, S of y1 yi star is equal to 1. Okay, there is only one block, right? If I have if it's n is infinity, right, there must be some blocks where it's 1, well, infinite number of them, and using the claim here, it's easy to see that it's defined an infinite sequence, right? I know that for length 1, there's only of length I, there's only one block that phi of sy 1 to yi and the star will be 1, and any subblock has to be 1 too. Right, so this is well defined, and if n is less than infinity, well, then I just take the block that is the same idea, right? Then we take alpha in the language be such that it has length n and phi of S alpha star is equal to 1. Okay, so then I have a map which sorry, so this ended there, right? So I have a map C from A hat to the Ott-Tomforde-Willis shift. Okay. Then, of course, there are many things to be proved. You have to prove that this finite sequence is in Ott-Tomforde-Willis, and you have to prove that this C is a homeomorphism. But it's nice. Now, this Ott-Tomforde-Willis subshift is really the spectrum of this commutative algebra. Okay, so there's the connection we are looking for, and but this is not right. Is a commutative subalgebra, but it's not the diagonal one. Okay, the diagonal subalgebra is the one generated by all the elements S alpha, PA, S alpha star, and I think here is where the inverse semigroup really would be interesting to look at. And now, okay, so if you want to this is again a commutative algebra. So to characterize it, you have to look at now the stone dual of this Boolean algebra. So the space of ultrafilters with the topology there given by stone duality. And what we can show is that this algebra is actually isomorphic to the locally constant function with compact support on this U hat. So that's really the space, right? That's where you used to do things, right? C of X cross to represent to get the groupoid, for example. If I want to get a groupoid representation of the algebra, you want to look at this space, and there is a shift map induced there on this set of ultrafilters, and which will give us the algebra. But this, of course, is much more. There's much more details, so I'm not going to get into all that. But
one little question: when the characters of the algebra A that you put before,
yes.
They are well, linear maps, so they are maps. They are induced, right?
The homomorphism, yes.
Yeah, A is as a module is freely generated by the S alpha star, right?
Okay.
And to say that something is a character as a an algebra homomorphism that goes to the ground ring is to say that you have the map defined in that basis and the multiplication rules are satisfied, right? Now, these multiplication rules, they look like, don't they depend on the semigroup structure of the S alpha stars? And couldn't they be so leading to an interpretation of the character space as a character space of the semigroup? Is there such a picture of that?
Yeah, okay, I don't know the
Because the multiplication rules,
right, it could be. Yeah, yeah, the multiplication rules with the semi-group here of the S alpha stars. But so what is so you want to do? Look at the character space.
I mean, the character space is the same as the homomorphisms, right?
Yes, yes. Yeah, the ultra filters, right? The ultra filters that we identify with the homomorphism into in this case 0, 1 into the ground field, as you said. But what's the end question again?
So, I mean, the homomorphisms from A to the ground ring can be if I understand correctly, multiplication in the algebra A is induced by multiplication in the semigroup of the S alpha star, right? So to say that something is an algebra homomorphism to the ground ring is the same as to say that the map restricted to the basis element is a semigroup homomorphism.
Okay.
So I can interpret A hat as homomorphisms of this. So is it the character? I mean, like, yeah, the characters of the semigroup, and whether I'm asking whether it's the full character space or you choose some, that kind of stuff that Rui does in his famous paper.
Right.
You have that picture in mind, but if you don't, it's fine.
Yeah. I'll have to look a bit. Yeah, I don't have. Yeah, it's a little bit. No, I'll have to look. I think it should be, but I have to. Right, the character there and. Okay. Okay. Yeah. I'll have to might mess up a little bit.
Okay, but then you say that you take a bigger, I mean, to have a groupoid interpretation, blah, blah, blah.
Yes.
The bigger algebra.
Yes, the bigger algebra. Yes.
So a bigger semigroup.
A bigger, yes, which is this one.
Yeah.
To get a groupoid. Yeah, we'll look at that one. You need these A's here. The span of SAT. And then it's also right the locally constant functions compact support on the stone duo of this Boolean algebra U, which is not such a nice space, but it is what it is. I mean, it is more general, right? Subalgebra, this subshift, sorry. But I mean, okay, so we have a grading. So some properties of this algebra has a grading as alpha p is beta star, a grading over z as usual. We can do a partial skew group ring description, and which is nice is that we can do it even without any topology. Look now, the subsets now there of the partial action is just going to be the C alpha beta, and we're really going to just send them to C beta alpha, and by raising beta and placing alpha in front, and we can just then look at the characteristic functions of these sets and get just algebraic partial action, and the associated skew ring gives it the algebra, so without any topology, or you can just put topology and get a topological partial action using the filters and all that, which is nice because then once you have the topological partial action on the set of the ultra filters, then you get the groupoid description, right? Once you have an algebra as a skew ring, partial skew ring of associated topological action, you automatically get the groupoid description, which we show that actually coincides with the Diacono-Renault system description. So there is there on that space you had, there is a shift, and we can then describe it as a Sternberg algebra of the Diacono-Renault system. Okay. Just before we end, I mentioned, right, that we wanted these algebras to be connected to the usual Leavitt path algebras and algebras of matrices. So the thing is, we define the unital algebra, and we know in general Leavitt path algebras, or they don't need to be unital, nor need the algebra associated with matrices, right, the XLOC algebras. So we define also a non-unital algebra, where we just take the Boolean algebra. It's again, right, we replace the Boolean algebra generated by C alpha beta, and now we get one does not contain the whole set X. So we do not allow alpha beta to be simultaneously the empty set. And then the subshift algebra now, the non-unital version, is again generated by partial isometries for each element of the alphabet, by projections for each element of this Boolean algebra, and we have similar relations, but we have to add these last two here, 4 and 5, that because we don't have the unit now. But now if this algebra is unital, this one that's here on the screen, then it coincides with the previous one that we defined. If you just start looking at this Boolean algebra generated by the C alpha beta, and somehow you get X there, then this algebra that we have here coincides with our previous algebra. If it does not have the X, then it's unitization. It's the algebra that we just showed. Okay, and this algebra, of course, is better suited for the Leavitt path algebras of infinite graphs and so on. So what we have is that we have a graph with no sinks and no vertex is simultaneously a source and an infinite emitter. Right, because look, our algebra really relies on follower sets, right? So there's a thing, if you want to see a vertex in the Leavitt path algebra, you kind of have to see it as a follower set of something, of an edge. Now, if you have a source, then it's bad. The subshift algebra does not like really sources. So if you have a graph with no sinks and no vertex that simultaneously at source and infinite meter, then our subshift algebra coincides with the Leavitt path algebra. And our point of view for infinite matrices was to look at ultragraphs. So ultragraphs, they generalize these algebras of infinite matrices, right? And then we also show that for ultragraphs for which every vertex is regular, then the subshift algebra and the Leavitt path algebra of the ultragraph coincide. Okay, so this here contains all the algebraic X-Olaca algebras here. Okay, in this proposition. And our main theorem was that we could describe conjugacy of the Ott-Tomforde-Willis subshifts, which is in terms of isomorphism of our algebras. Even though the space is smaller, right? This Ott-Tomforde-Willis is a projection of this some kind of projection of this bigger space of the ultrafilters. If you have a homomorphism, we can describe, if you have a homomorphism between two Ott-Tomforde-Willis subshifts, we can describe it when this homomorphism is a conjugacy, right? In terms of isomorphism of the algebra. And well, okay, so it's a little bit technical. I don't want to get into much of it, but we find this is a if and only if. And describing conjugacy in symbolic dynamics is a very hard problem, right? So this is a result that we found interesting. So if you have a conjugacy of Ott-Tomforde-Willis subshifts is the same as an isomorphism of our algebras that preserves diagonal and has, and there are certain projections that we're doing here, they're commuting, but we can also describe it as in terms of isomorphism of the cover space. That's the word, right? The bigger space. So this would be just really a conjugacy of the bigger space. So to have a conjugacy of the space of the ultrafilter is the same as having a conjugacy of the Ott-Tomforde-Willis subshifts, and same as having an isomorphism of the groupoids, well, such that a few more
What are the pi maps?
Sorry?
The pi maps, what are they? Pi
right. Yeah, they're defined in the paper. I think maybe let's see if I can I say what are the pi maps? I think they're a little bit, they're just
If it's too complicated, it doesn't matter, but since they appear there.
yes. The pi maps are projection. It's the projection of the bigger the bigger space into the Ott-Tomforde-Willis space, of the U hat into the Ott-Tomforde-Willis. So into the spectrum of the bigger commutative algebra into the spectrum of the smaller one. Okay. There's so many there, sometimes I have to remind myself. Okay. And so this also means that we have a Z-graded diagonal isomorphism of the algebras. Okay? So these are the main result of our papers. Like we could characterize conjugacy here in terms of, well, of these isomorphisms of the algebras. Right. So so now, as I said, we are now currently working with the sister algebras, which one thing that I didn't say is that these algebras, they can be labeled space algebras. So if they have results for label spaces, you can apply them here for label space algebras. But for example, for the sister algebras, we are hoping that to add here something with K-theory, right? Because then for algebras, for Leavitt path algebras, the K-theory is very hard. But for sister algebras, I think Posk and others, I think they have computed the sister algebras of labeled graphs already, of labeled graph sister algebras. So I'm hoping that we can add something with K-theory here, but that's current work in progress. Okay, so that's what I had for today.
Okay, thank you very much, Daniel. I want to ask one question, since we are here. So doesn't don't you have a homomorphism? Doesn't the shift induce a homomorphism of this space U hat? Because yeah, in here you have a homomorph.
They're counter sets, so they have they're homomorphic. The thing is, if it's a conjugacy, right?
Yeah. So, but can you have a conjugacy between, because the U hat spaces are bigger than the OTW spaces, right?
Yes. Yes.
And so this theorem is formulated in terms of a conjugacy between the OTW spaces. But couldn't there be a conjugacy between the U hat spaces? And in that case, maybe a similar description, a similar equivalent list of equivalent conditions without the any pi's would be obtained. That's one.
Right, before the projection.
Because the projections are there, so that the shift, the conjugacy.
Yes, I believe so.
In the OTW spaces, which are smaller.
Right, exactly. Yeah. If you just start with a homomorphism of this U hat. And here we have the pi's, which are the projections. If you just have the, yeah, I think so. Well, then I think yes. Yeah, we should have, right? Because then we have the groupoids. I didn't write the conditions for the groupoids, but here should be also. But I think so. I think we might be able to get results without the pi's and descriptions. So yes.
Okay, so sorry, I monopolized the questions. Are there? Does anyone else have a question? Well, if not, we thank Daniel again for his very nice talk. And we are done for today. I will stop the recording now.